Hi everyone, welcome back to a new video of this series where I show you guys what my equation sheet was for the physics portion of the MCAT. Before starting, just want to make sure and clarify that these equations that I'm going to share with you based on the chapter are not all the equations that could be tested, but according to the Kaplan textbook and according to my experience, these are the equations that are the most important for you to know. And these same equations I'll share with you guys from this equation sheet allowed me to average a 130 in the full lengths I have done so far in the Chem&Phys portion of the MCAT. So without further ado, let's start. Today the chapter is going to be Chapter 7 of the Kaplan study books, which is about waves and sounds. So the first important equation would be the speed of wave, which is the frequency times the wavelength. Frequency is has a unit of 1/seconds or hertz, and wavelength as a unit of meters, which gives us the speed of wave in meter per second. We also have the angular frequency, which is just another way to represent the frequency, which can be obtained with 2 pi times the frequency. And it's going to be in rad over seconds, which makes sense, right? Frequency is seconds, 2 pi is going to give us rad. This also, T, I have not shown you guys, but T is basically a sign for the period, and period is obtained with 1/frequency. So if we isolate frequency, in that case we would have 1/T. So if we replace then frequency by 1/T, we would obtain this here. So that's another way to get the angular frequency. All right, next, the speed of sound. First off, the speed of sounds in air at 20 degrees Celsius is 343 meters per second. But there's another way also to obtain it, which would be to take the square root of the medium's resistance to compression, which is capital B here, divided by rho, which would be the density of the medium. So the speed of sound would be the square root of the resistance of the medium divided by the density of that medium. And obviously don't forget to do the square root of that. So that would also be in meters per second, since it is the speed, so speed of sound. Now the next one would be the Doppler effect, which is one of the most important equation in this chapter. This basically states that the frequency will be altered from the original frequency if whether the source or the observer are moving towards or away from each other. So here we can see that the frequency of observer, so the final frequency would be the frequency of the source itself times the velocity plus or minus the velocity of the observer divided by the velocity plus or minus the velocity of the source. And this will make sense because if the frequency of a source is a certain number and the source is moving towards the observer, then it would only make sense that the frequency that the observer is going to experience is going to be greater than the actual frequency of the source, right? So this is why there's a plus or minus. The tricky part here is whether if the observer is moving towards the source, we know that it's going to experience a greater frequency, and if the source is moving towards the observer, we know that the observer is going to experience a higher frequency. So in the case where the observer is moving towards a source, then we would have the velocity of the sound plus the velocity of the observer, because we're going to obtain a bigger fraction, so we multiply it by the original frequency to give us a higher frequency, because the observer is moving towards the source, so it's going to experience a higher frequency than the original one. If, in the other end, the source is moving towards the observer, the observed frequency is also going to be higher, but for a higher observed frequency, we would need a denominator. We would need a smaller denominator, which is why if the source is moving towards the observer, we do not add the velocity of the source like we did with the velocity of the observer, but we will subtract it, because a smaller denominator is going to give us a larger fraction, which is going to give us at the end a larger observed frequency. I suggest, if you didn't understand the way I explained it, to go whether in the Kaplan book or study it a little bit. It's going to make sense, and then come back to this equation and then re-listen. It's going to make a lot of sense, and then that's going to make it a lot easier for it to stick and for you to remember it. Now, the other another equation would be the intensity of sound, which is the intensity, which is in watts over meter squared, is equals power over area. This makes a lot of sense. Again, in physics, you can guess what the actual equation is going to be just at looking at the units. You know, watt is a unit of power, and meters squared is a unit of area. So here, intensity of sound is power over area. Okay, another equation here would be the sound level. The sound level is in decibels, and it basically is the initial sound level plus 10 times log of the final intensity divided by the initial intensity. We talked about the intensity of sound in the previous equation. We can then use the previous equation to find these variables and then plug it in, and then this is going to give us the final sound level. And to wrap it up, we'll have the harmonic, which is also another important subject in this chapter. Harmonic is basically the number of half wavelengths supported by a string in this case, but there's different harmonic. There's also there's harmonic that are attached on both sides, which would have a node on both sides. There's harmonics that have antinodes on both sides and on both ends, if you want to call it. And then there's which would be called here open pipes, and then there's closed pipes, which have one node and one antinode. So here, for a string where we have this part here attached and then this part here attached, we would have the fundamental harmonic, which would be n equal 1. And here we can see that a full wavelength would be to go up and down and then arrive here, right? So a full wavelength is going all the way and then coming here, another node. So here the fundamental only makes sense that the length of the fundamental harmonic would be the wavelength divided by 2, because that's half of a wavelength here. Now if we go to harmonic number 2, we know that here we have 1/2 wavelength, here we have a second half wavelength, which makes a full wavelength. So the length of this harmonic would be one wavelength. For the third harmonic, one half wavelength, two half wavelength, three half wavelength. So we know that the length here is 1.5 wavelength, or 3/2 wavelength. And if we isolate wavelength, we will this will make sense that the wavelength can be calculated with the equation 2L/n, which is the harmonic number, 2L/n. Now, for an open pipe, we have antinodes on both sides. And then we know that for a full length, we would need, so if we start here, we would need to go back to this same spot on the other side for it to be one wavelength. So we know that if we go here and then end up after half of a wavelength, then the length of this harmonic is wavelength over 2, or half of a wavelength. For harmonic number 2, there's 1/2 wavelength here and a second half wavelength here, making the length of it one wavelength. An n equals 3 harmonic would be 1/2, 2/2, 3/2, so 1.5 wavelengths. And then we can see that if we isolate the wavelength again, we obtain the same equation as above, 2L/n. So a string with nodes on each side and then open pipes with antinodes on each side, you have the wavelength equation as being the same, so 2L/n. So the difference here is with closed pipes. So closed pipes is basically, on one side you have a node, and then on the other end you have an open pipe, which has an antinode. Now we have, and then the length of this is, obviously we know that if we go up and if we would go down, in this case that would be half a wavelength, so we're even smaller than half a wavelength. So here the length of the first harmonic for a closed pipe is wavelength over 4. And then we jumped right away to harmonic 3, because if we would have harmonic 2, then we would have a quarter wavelength, half a wavelength, and then this part here, we remember, would give us this part here, right? Would give us the fundamental one. So for closed pipes, we only have impair or odd harmonics. So in this case, we know with closed pipes, we count it as being a quarter wavelength. So we have 1/4, 2, and 3. So the length of it is 3/4 over 4, or no, 3 wavelength over 4. And then we go to the next odd number, which is 5. So 5/4 basically. 1, 2, 3, 4, 5, 5/4. And if we isolate, in this case, if we isolate the wavelength, we would have 4L/n, which is always an odd number, and is the harmonic. So I hope this helped. This is all I got for the important equations on waves and sounds. And thank you for listening. I hope this helped you.